Good evening. This is Team 8. Members include Brittany, Bujin, Abel, and Richard. We'll be talking about the axial wind turbine. Technology is continuously improving, and as well as the demand for cleaner energy. One of the most abundant sources of energy is from the wind. The team has decided to focus on the vertical axial axis wind turbine, also known as Vawt. We chose this option based on the usefulness and how it can be applied in the urban settings. So essentially, Vawt is divided into two parts, Sibonius, which is a vertical axis wind turbine, and Sibonius, which is a horizontal axis wind turbine.
Thank
For our
you.
team project, various models simple manufacturing design, meaning it's easy to make. The drawback of the current design is low power output, and it has a negative torque on certain areas. Our new design is pretty much to improve on those. And to do so, aerodynamic performance of the VOT from CAD design was tested. The modeling of the design was done by using Autodesk Inventor and SOLIDWORKS, which we were able to run a flow and pressure analysis. And various tests showed improvements and feasible proposal to an actual application in more urban areas.
The problem of this project was to take a vertical axis wind turbine that had been known to function off receiving contact on one blade to where it receives contact on each of its blades. To address this issue, the blade and the overall structure will be designed to where it can extend and retract from the hub, optimizing the torque it receives on the turbine shaft.
The objective of this project is very straightforward. First, it is to determine the amount of energy that is necessary to meet required standards and size the system to the specifications. Then create an adjustable diameter that can change with different wind speed and angle. After that, we ensure the hubs and shaft can support the structure and loads, and also figure out the method to increase the life of the shaft and bearings.
Turbines operate on a simple principle of converting kinetic energy from the wind into mechanical energy. The contra-rotating blades have been recently been tested to improve vertical axis wind turbines. The contra-rotating blades have been used in the past to enhance the performance of turbines in terms of both power and torque. A maximum power and torque coefficients of 40% and 43% were respectively possible with the dual rotor system. This is a concept that can be incorporated into our model if we get it into significant gains on our power and efficiency. Uh, in terms of the model was created in Autodesk Inventor due to its ability to formulate the rotating blades and structure that could extend and retract from the hub. This was also created. This was also used to create the shape and assemble other parts cohesively. This design makes for easy manufacturing and installation. The results were displayed using Inventor simulation and SolidWorks. Uh, the we also A simulation was also ran in the z coordinate axis direction to see how velocity would be affected as the wind turbine blades were in motion. The shear stress and pressure graphs were also populated and simulated. This assisted uh, to gain knowledge in how the wind turbine was to be affected by wind and how well the material would hold. The procedures needed to finalize this report were also displayed to the Gantt chart in the appendix section. This concept will contain an extendable shaft, which will enable the turbine to have a greater sweep area, supplying a higher amount of energy to be absorbed from the wind, in addition to a larger amount of torque. The shaft in this design is expandable up to 20.32 centimeters, increasing the overall diameter by 40.64 centimeters, which is double the original diameter. While the shaft arms are extending, the arc angle between the upper and the lower rotor are about plus or minus 8. This is necessary for the blade to maintain a consistent orientation. The design can be seen in the later slides.
So, when designing our VOT, there's several things to consider. Aerodynamics improves as the number of blades increases, When moving from 2 to 3 blades, there is a 3% increase in efficiency, but when moving to 4 blades, the gain is marginal at 0.5%. We also have to take into account the cost of the system increases significantly by increasing the number of blades. So we determined the number of blades in our system to be 3. In a lift type turbine, the driving force of the turbine is when wind force blows over the airfoils, kind of like an airplane wing. The lift force is perpendicular to apparent velocity of flow and is increased with the angle of attack. The lift force is there's another component, the drag force, which is undesirable. It's actually tangential to the lift force. So while the lift force supports rotation, drag force actually opposes it. So the performance is at its best when the ratio between the two is optimum. The blade rotates around the axis, so you can imagine that the angle of attack varies. This means that there are areas in which the drag forces are high. We have implemented a helical blade design to combat this issue. So as the turbine rotates, there's always a section of the blade with optimum lift to drag ratio. To find the sizing, we basically work backwards. We started by determining the average power usage by typical household. So then we use the power output equation and solve for the swept area. From that, we establish a proper diameter and blade length. All the other components were sized to accommodate a sturdy structure, which we will discuss later in the results. So now I will discuss the innovation. Next. Our innovation was to design a Vawt with an extendable, retractable blade support system. Our design can increase the rotor diameter by about 40 centimeters or 29%. So what's the benefit of expanding the blade diameter? In the previous slide, I mentioned the wind power equation. From that 1/2 rho AV cubed, we can see that the only variable we can manipulate is the swept area. This allows for more energy from the wind to be able to be captured and thus increasing the power output and torque. In addition to capturing the energy from the upwind blades, you can also catch some energy from the downwind blades on the backside. The upwind blades extract most of the energy, typically 80%, so the downwind is much slower with less energy. Increasing the rotor diameter allows for more space in between the blades, which could also potentially get a better wind quality on the backside. And now Brittany will discuss our analysis results.
The design was created to populate the results with the rotation of the blades and structure that can extend and retract from the hub. In the figures displayed, we see the analysis of pressure and velocity on the overall assembly is taken into consideration, and the velocity in the z-coordinate axis direction is displayed. Next. Here in these figures, we show that the shear stress upon the supports, and we also show that the pressure applied by the length. Next. Here we have our calculations. In the calculations, we are able to calculate the amount of power provided by the wind displayed in the first set of equations. Below are the second set of equations where we determine the diameter across the turbines is 1.411 meters contracted and 1.812 meters expanded with a blade length of 2.291 meters. Next. Here we have our efficiency of the turbine losses. Mechanical losses due to blades and gearbox is 0.3%, electrical losses is 1%, and the wake losses is 3%, with a turbine efficiency of 35%. Here we also display our power output of the turbine. Next. So here we have our tip speed ratio, which is 6, and we can see our torque contracted is 11.729 Newton meters, and our torque extended is 19.505 Newton meters. Here's our cost analysis. This is just an overall breakdown of what we were able to conclude from our project. This is displayed for you to view. And in conclusion, we have, from this experiment, we confirm that the Vawt system will not fail under moderate conditions and can provide an increase in net power output. By having a design with the ability to extend and withdraw from the hub, the maximum possible energy that can be obtained from the wind increases. This allows the turbine shaft to be optimized dependent on the varied environmental conditions by allowing an increase in torque to be acquired. With our FEA analysis, we were capable of improving the design by identifying weak points. This allows us to determine increasing size and thickness of the shafts, hub supports, and to improve the overall longevity of the system. Next. Here are our references, and thank you for your time.